Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last few lectures, we were discussing about stochastic user equilibrium, and today we will be discussing one algorithm called method of successive averages to solve that stochastic user equilibrium problem. So, if you remember, in the last class, we had ended with the discussion that approaches like convex combination algorithm are not preferred for solving stochastic user equilibrium because the move size step that is involved there can become very computationally burdensome because the move size step involves having a closed form expression for function z, and since that function z, which is the objective function, also has one term related to the expected perceived travel time function, and that might involve some path enumeration. So, evaluating that might not be a very computationally efficient method. Okay, so that's why we'll be looking at an alternative method called method of successive averages. So, in short, it is called MSA. So, the difference here is that in this method, a predetermined move size along the descent direction is chosen. So, what it means is that alpha n is not determined on the basis of some characteristics of the current solution. So, in the convex combination algorithm, we had solved an optimization problem to determine alpha n once we knew the auxiliary solution yn, given that you know what the current point you are xn. Okay, so if you remember, once we had founded yn in the descent direction step, so after that we wanted to determine alpha n. Okay, and for that we had solved this optimization problem, minimize z, which is having argument of xn plus alpha n times yn. Okay, where alpha n goes from 0 to 1. Okay, so the difference here is that in this method of successive averages, we will not be solving this optimization formulation to determine alpha n. Rather than alpha n will be given to you before you start the problem. Okay, so for example, alpha 1, alpha 2, alpha 3 and so on, for every nth iteration, what alpha to choose will already be given. Okay, so that is kind of the difference from this convex combination algorithm that we had used for solving the deterministic user equilibrium problem. Also, one thing to remember is that if any assessment and so on, only user equilibrium problem is mentioned, so then it automatically means the first basic version of the user equilibrium, that is the deterministic user equilibrium that we had referred to. Now, this method of successive averages will only converge to the optimal solution if the objective function that we are trying to minimize satisfies some conditions, and also we cannot just use any arbitrary values of alpha n in this algorithm. The values of alpha n that we choose, or the move sizes that is called, should satisfy some conditions. Okay. So, for example, this objective function should be twicely continuously differentiable. Okay, and its gradient should vanish only once in the feasible region. Okay, so these conditions are ensured for the objective function of stochastic user equilibrium, but we will not be testing them here. And also, the move sizes should satisfy the following. First is this, that the summation alpha n, where n goes from 1 to infinity, should not be finite quantity. So, this ensures that the algorithm does not stop prematurely, and this condition, that summation alpha n square should be finite. Okay, so this ensures that the variance of the solution diminishes as iterations progress. Okay, so we will not be looking for the derivations of this condition, that why this will ensure this and why this actually ensures that the variance of the solution diminishes, but let us just know that there are some conditions that should be respected by the move size that we choose. We just cannot choose any arbitrarily move size. Okay, so we should be aware that there are some conditions that are to be satisfied, and those are some conditions here. Okay, so one of the simplest move size sequences that satisfies these conditions is alpha n equal to 1 by n. Okay, so this is then giving us the whole information of what move size to choose. For example, we have the first iteration, we have alpha 1 equal to 1, then alpha 2 equal to 1 by 2, alpha 3 equal to 1 by 3, and so on. Okay. So with this sequence, the nth iteration of the algorithm should be as follows. So the solution in the n plus 1 iteration is equal to the solution in the nth iteration plus alpha n times this descent direction. So we had already seen this equation before. Okay, so now instead of alpha n, we have replaced it by 1 by n. Okay, that is only difference. And if you remember, dn actually is yn minus xn. So yn is the auxiliary solution that we find in the direction finding step. Okay. Okay, so what we will be doing in the next step is that we will be taking the terms corresponding to xn together. So we will be having xn times 1 minus 1 by n plus 1 minus n times yn. Okay. And just one more thing is that this yn is actually coming out of this expression here. So since this is the case of stochastic user equilibrium, so between any OD pair, there is a probability of choosing that particular path in that OD pair. Okay. So if you remember what is PKRS, PKRS is the probability that the kth path has the lowest perceived travel time as compared to all the perceived travel times of different other paths which are connecting R to S. Okay, so what is the probability of that happening? That is PKRS. Okay, so since the perceived travel times of different paths which are connecting R to S are having random distribution. Okay, so these are random variables. So we cannot just say that this is the path that has the shortest perceived travel time, because these perceived travel times for all of these different paths are random variables. Okay, so we can only tell that what is the probability that the perceived travel time of this path will be less than the perceived travel time of all the other paths. Okay, we cannot just say with certainty that the perceived travel time of this path will always be the shortest. Okay, so that is why we had seen that FKRS is equal to QRS times PKRS. Okay, this equation we had seen in the case of stochastic network loading also, and then it got extended for the case when we had the stochastic user equilibrium formulation also. Okay, so this is the total travel demand from R to S. Okay, and this is the probability of choosing the kth path from R to S. So this is how we get the flow on the kth path connecting R to S. Okay. So therefore we have the probability of choosing a particular path k from R to S at the nth iteration. Okay, so that this quantity gives us this flow in the path k connecting R to S in the nth iteration. Okay, and then we can use the relationship to find the flow through any link A after the descent direction step. So suppose we have done stochastic network loading, and these are the probabilities of choosing different paths that we got. Okay, now we already know that these are the parameters which connect how the flow on links are related with the flow on paths. Okay, so this is equal to 1 if link A is part of the path K connecting R to S. So we use this to determine the flow through link A in the nth iteration. Okay, I mean this is the auxiliary solution that we just get after the direction finding step. So this is PKRSN is what we had obtained if we do any direction finding step, and with this we can calculate the flow on every path k connecting R to S, and then this is actually summing the flows of all of the different paths that are passing through link A, and then it is giving the flow through link A, okay, in the nth iteration. Okay, so now coming back to this equation, so if you recall, we said that we will be taking all the terms corresponding to xn together. Okay, so this is what we get, because this is the same as 1 minus 1 by n. Okay. Okay, now what we can do here is that the way we have this equation, if you suppose substitute instead of n plus 1 n, so you get xn equal to n minus 2 divided by n minus 1 x n minus 1 plus 1 upon n minus 1 y n minus 1. Okay. So now we can substitute this here, and when we do that, this is what we get. Okay. So we'll be multiplying n minus 1 by n to this, and therefore this is the one term that we get, this is second term, and this term is coming as it is from here. Okay. Now these two terms can be written in like this, because this n minus 1 will get cancelled to this n minus 1. So we take 1 by n outside. Okay. Now again this xn minus 1 can be replaced by an expression like this, where instead of n we replace by n minus 1. Okay. So now if we keep doing this, then what we will be getting is that in the end we will be having this 1 by n summation while where L goes from 1 to n. Okay. Thus the solution at each iteration is the average of the variables y in all the preceding iterations. So this is saying that the solution in the n plus 1 iteration is equal to the average of all the auxiliary solutions that we got in the previous iterations. Okay. Okay. So that is why this method is called the method of successive averages. Okay. So let us summarize this method of successive averages as follows. So first we have an initialization step here. So if you remember, in the convex combination algorithm, which is an iterative algorithm, we wanted to start with one initial solution, right? Now this initial solution should be a feasible solution. Okay. So solution in terms of any traffic assigned problem refers to how the flows are getting assigned on different links and paths. Okay. So if a solution has to be feasible, so the main constraint that we need to be really worried about is that the sum of the flows on all of the paths connecting an OD pair should sum to the travel demand on that OD pair. Okay. So that is why, if you remember, in order to find the first initial solution in the convex combination case, we had, when we do all or nothing assignment, then we ensure that the flow between every OD pair is assigned to that path which is having the shortest travel time. Now that automatically ensures that the sum of the flows on all of the paths connecting a given OD pair is equal to the travel demand of that OD pair. Okay. So when we do that whole process, so in the end we can ensure that whatever link flows that we calculate after that procedure, then this whole solution will be feasible. That is, the sum of the flows on all of the paths connecting an OD pair will be equal to the travel demand. Okay. So again, in this method of successive averages also we need to start with some initial solution. So we will be performing the network loading step here. So in the deterministic user experience problem, the network loading step was all or nothing assignment. Now in this case, the network loading step is doing this stochastic network loading. Okay. So we have seen different kinds of stochastic network loading in the previous lectures. So one was, if we assume that the distribution of the error terms is suppose given by IID Gumbel variate, so then we can use a logit route choice model. If we assume that the error terms are normally distributed, so then we have probit choice model and so on, right? So we need to decide which kind of route choice model we are using. That is, equivalently we need to decide that what assumption we want to make on the distribution of the error terms. Okay, so we need to decide that will define what network loading procedure we use, and what we require else is that once we have suppose decided that let us use the logit route choice model. Now in the determination of the probabilities of choosing different routes in the logit route choice model, you have like expressions like this: probability of choosing the kth path is equal to e to the power minus theta times CKRS, where CKRS is the major travel time of path K connecting R to S, divided by this summation e to the power minus theta CLRS, where L is the set of all of the paths which is connecting R to S. So we need to know the values of these major travel times on different paths connecting an OD pair, CKRS. Okay, so now how to start with one set of major travel times here? So if you remember, if it is the case of deterministic user equilibrium, so major travel times are the deterministic travel times. Okay, and when we were doing all or nothing assignment, what we had done is that we had set zero flow on all of the links, and that gave us the free flow travel times. Okay, and those are represented by this. So this 0 is actually telling that the flow on each link is equal to 0. Okay, so we can again do that now. So we can again put the flow on every link to be equal to 0. That will give us the free flow travel time on different links, and those can be used as the set of major travel times on these different links in the beginning. Okay, so those are the initial major travel times. Okay, so now that we have specified that what route choice model we want to use, that is what assumption we want to make on the error distributions, and we also have started with some initial values of the major travel times by assuming them to be equal to the free flow travel times. So now we can actually calculate the probabilities of choosing different paths connecting every OD pair. Okay, and once we know those probabilities, so then we can use this relationship that the flow on path K connecting R to S is equal to QRS times PKRS. So once we determine PKRS from this kind of expression, if we are assuming suppose that it's a logit route choice model, so we can determine the flow on path K connecting R to S by this expression here. Okay, so we do this for every path connecting R to S, and then we do this for every OD pair RS. Okay, and then after that, once we've determined the flows on all of the different paths connecting different OD pairs, we can determine the link flows. And how do we do that? So we have seen that the link flows can be determined from this relationship that XA is equal to this triple summation we have R, S and K, FKRS times delta AKRS. Okay, so this delta AKRS relates whether a particular link K is part of the path K connecting R to S. So with that information, we can calculate the flow on every link K. Okay, so at the end of this procedure here of this stochastic network loading, we get the flows on different links. Okay, so if you look at the all or nothing assignment also, the output is the same, that is both all or nothing assignment and this stochastic network loading are giving you the flows on different links or across different paths. Okay, and actually this stochastic network loading is an extension of or more generalization of the all or nothing assignment. So if there is no uncertainty that is present across the travel times on the network, the solution of the stochastic network loading will give exactly the solution that you will be getting from all or nothing assignment. Okay. Okay. So from the output of the stochastic network loading model, we get the flows on different links. Okay. Now what we do here is that we can now put these flows on different links in the travel time functions. So these will give us the travel times on different links at the nth iteration. Okay, so in the beginning we set n equal to 1. Okay, okay, so now that we have some updated travel times on different links TAN. Okay, so now we can implement this direction finding step. So the step 0 that we were executing was an initialization step. Okay, so that step will not be executed again and again. So since we wanted to start with some initial solutions, so that's why we implemented that, and we wanted to start with some initial solution to be feasible. So that's why we decided to do this stochastic network loading, okay, which is actually becoming equivalent to all or nothing assignment if it's a deterministic user equivalent case. Okay, so now this is the main direction finding step. So now this is the equivalent of finding the solution yn. Okay, so if we remember, we had this step in the convex combination algorithm also. So there we used to do all or nothing assignment. So now instead of all or nothing assignment, we are doing the stochastic network loading procedure. Okay, and the input for the stochastic network loading procedure is the set of the measured travel time on different links, which this value is coming from step 1. Okay, so in the step 1 we had calculated the updated travel times on different links. So we will be using that as the measured travel times of different links here. And again, we will have to decide what route choice model we are using. So whatever route choice model we had decided before, if it was logit model, so then logit model will always be the case here. So with that, we can again then calculate the probabilities of choosing different paths connecting every OD pair. So we will be getting PKRS for every path K and RS, and then we can determine the flow on every path K connecting R to S by this equation here. Okay, so this will give the flows on different paths, and then we can calculate the flows on different links again. Okay, now instead of XA here, I will be representing by YA here, because this is the auxiliary solution that we are getting. So this YA will be equal to, again, in the same way, I mean, how we connect the path flows to the link flows, okay, by using this parameter delta AKRS. Okay, so at the end of this step, we get auxiliary link flows, which is given by this YAN. Okay, so now that we have determined this YAN, we can now determine the solution in the next iteration. Okay, so if you remember, this is the equation that xn plus 1 is equal to xn plus alpha n times yn minus xn. Okay, now alpha n in this case we have decided to keep 1 by n. So this is predetermined. So in the method of successive averages or MSA, we don't need to do an additional step before this one to determine alpha n. So since alpha n is already given, so now we can execute this step. Okay, so this step is executed for every link A. Okay, so these are the vector notations here. Now this means that for every link A in the next iteration, the flow will be equal to what was the flow in this link at the nth iteration plus 1 by n times yn minus xn. Okay, so this equation is for every link A. Okay, remember that. Okay, so now that we have got the solution in the next iteration, so we want to now decide that whether we should stop here or not. So if whatever convergence criteria that we set in the beginning, if that is reached, then we stop. If that is not the case, then we set n to be equal to n plus 1, and then we go to step 1. Okay, so step 1 is the step where we will be now again calculating the updated travel times. Okay, so here if convergence is not reached, we already have the new solution xn plus 1. Okay, now we can put that back again into the travel time function. So that will give us the new travel times for different links Ta n plus 1. Now these are some constant fixed values. So now then go to step 2 where you can execute the stochastic network loading. So these travel times, you keep them as the measured travel times of link A. Okay, so this you get for every link A, and then whatever route choice model we are using, we can use that to determine the flows on different paths, okay, by determining the probabilities of choosing different paths, okay. And then once the path flows are determined, we can calculate the link flows, okay, and then so on. So this algorithmic framework of method of successive averages that we just saw can be applied in conjugation with any of the stochastic loading models, like whether you want to use the logit stochastic loading model or the probit loading model, it does not matter, okay. So this is saying that the auxiliary link flows are obtained in step 2. Step 2 is the one where we are finding the descent direction, okay, where we are using the stochastic network loading from the path choice probabilities like this, okay. So this is saying the same thing that what I told you, that once you determine the probabilities of choosing different paths between every OD pair, then you can calculate the flow on different paths, which is QRS times this PKRS, okay. And once you have the flows on different paths, then you can use this parameter lambda AKRS, and then you can sum it over all the OD pair RS and over all the paths to get the flow through link A in the nth iteration. So this is just the same way of saying that the flow through link A in any iteration is equal to sum of the flows of different paths that are passing through that link. So this is what it says mathematically, okay. And one thing is that here in the argument of this probabilities, there is CRSN here, okay. So this is the vector of the major travel time that we have at the nth iteration. So this is actually obtained from the step 1. So when we do this TAN equal to this, okay. So this gives us the major travel time on different links, and once you have the major travel time on different links, you can calculate the major travel time on every path connecting R to S. Then you just sum the flows of all of the links that are there in this path, okay. So for every link A which belongs to this path K, you sum the major travel times, okay. So this is how you will be getting the major travel time of every path, and then you can put that into the expression for the probability choice. So if it is being assumed that we have logit route choice model, so then you have closed form expressions for determining the probabilities of choosing different paths. If it is logit route choice model, then you can use the expressions that we have for the probabilities, and if it is probit choice model, then one can use the Monte Carlo simulation to determine that, okay. So with this we will be ending the lecture here. Thank you.